Okay, so welcome everybody. So we are here with JoshuaDorrington, that is a Marie Curie postdoc fellowship from University of Bergen, and we have been working together in the past when in Germany in the framework of the project Waste to Weather, and that's the time when we met together, and we shared the interest of understanding the dynamics of extreme precipitation. So we were working together on this topic. That's why Joshua was in this trip from EGU to ATH, decided also to stop in Bologna and to have a chat and keep the contact and on this. So I was thinking that it was cool for him to have a seminar here, because with an encircle project we had nice things to share and kind of mutual interest, I would say, in this topic. What else to say? PhD Oxford University, then postdoc at KIT. And the floor is yours. Thanks.
Thank you. So yeah, so this is a kind of a composite of different talks. So that's why this is from my EGU slides. I only have my Bergen co-authors on here, but also work I've done in collaboration with Federico and with Christian Graham and with Mark Spencer and lots of other great people. So and I'm going to be talking about what we've been doing in the last sort of 4 years, trying to understand how we can use dynamics to improve our understanding of extreme events, mostly extreme rainfall, both in terms of interpreting forecasts, but also in terms of understanding what climate models are doing, maybe calibrating projections of climate models, and also a little bit on trying to understand where the signature of climate change lies in influencing extreme events. If that's beeping, does that mean there's something happening on Teams that's no?
It's more people connecting.
That's fine.
Yeah.
All right. Cool. So that's not relevant. Let's get that. Okay, so I'm going to sort of start by talking a bit about the climate stuff, I think, and then I'll bring in the weather stuff and then the attribution stuff. So what's the motivation? I mean, obviously, if you're on a weather timescale, we don't need much motivation to think about why extreme rainfall is important, especially here in Bologna. I don't have to explain that. But also, this is a topic that increasingly is becoming relevant for climate. Increasingly, there's a demand for climate information on weather, time, and spatial scales. A little example I picked up here is this is the front cover of the Voss Kommune Klimareport for basically for the region of Voss in Norway. This is how they want to, this is how climate change is going to impact their river valley and their town. For those who aren't familiar with the geography of rural Norway, Voss is an area of about 40 by 40 square kilometers with 25,000 people, and they have their own climate report. And they come to us and they want information about how are we going to be affected by climate change? Will extreme rainfall be more likely in our valley? And answering questions like this are really like pushing the limits of what we can simulate with the models we have. So to try and tackle this increasing complexity, we're making our models more and more complex, and our model graphics are getting more and more complex. So these are from, I think, CNOTE 7 sort of concept papers. The left is showing all the different components that go into a modern climate model. I mean, even enumerating all of these would take a lot of conceptual load, let alone understanding how they all interact and what the grand narrative is that they provide. And then also on top of that and alongside that, we have a sort of nested series of models, regional models inside global models and impact models inside regional models. And the pipeline to go from developing new climate scenarios to putting information about climate impacts in people's hands is apparently less than one PhD project in time. So we're having to deal with larger data sets than ever, faster than ever, and try and extract some usable narrative from them. That only gets even more severe when we consider some of the sort of newer kinds of simulation out there. So we've got Destination Earth, this attempt to simulate the entire Earth at 1 kilometer for decades at a time. They're going to put out a petabyte of data every single day. So how are we going to process and analyze that? And then we have the sort of more conventional large ensembles, where now you might have hundreds of realizations of centuries of climate. So yeah, how do we work with these data sets and telling us? Skip that one. So the approach we're using is to focus, and I don't know why this slide's in all caps, it's a bit intense, so just imagine it isn't. We're focusing on the synoptic processes because if you want to understand how global climate changes impact the local scales, it's the synoptic processes that are the direct causal link between them that kind of provide the glue from which you can assemble a coherent narrative. So lots of people have worked on trying to understand how we can understand extreme rainfall in climate simulations based on dynamics. There's lots of different approaches. You can sort of decompose, so you can say rainfall is a combination of moisture and ascent, and you can decompose it in those terms. You can take regime-based approaches. You can take analog-based approaches. But all of these have, none of these quite capture everything you'd want to understand about daily rainfall. And part of the reason of that is that rainfall's a kind of awkward variable, right? So it's very variable across time and space. The dynamics that drive rainfall can differ drastically across small regions, especially in strong orography. Decomposing things by thermodynamic moisture and dynamic ascent can be problematic because synoptic dynamics blend those two together by connecting air masses with different properties around. And also approaches that leverage sort of dominant variability modes aren't necessarily going to perform well at explaining extreme events, which by definition are not part of the dominant variability of the atmosphere. So we've been developing an approach based on flow precursors, which are sort of targeted to particular kinds of extreme event that we're interested in. Are a multivariate representation of the atmosphere, combining information at different levels and different variables, and which are locally defined and vary across season and region. And so part of the incentive originally, I said that we can nicely introduce the sort of history of how we came into this work, and we started with the weather problem. And basically the problem we were dealing with is, well, how do we interpret, how do we learn from an ensemble forecast? So nowadays, the IFS extended range forecast is 100 ensemble members every day. So here are 100 forecasts of vapor transports over Europe, and embedded in here are about 10 or 12 high-risk scenarios for North Italy, but you might struggle to see those, even if I gave you quite a while to look for them. And certainly if you're an operational forecaster, going through all the various ensemble members and scenarios inside the forecast is not really practical. So we need some way to sift this information and highlight the most relevant parts. So how do we proceed? The core of our approach is we basically start by defining some sort of time series of events we're interested in. In most of what I show today, it's going to be, was there heavy precipitation, by which I normally mean 95th percentile daily precipitation, aggregated over a spatial region? And I go to era 5, or your other favorite reanalysis product, and you say, well, what was the large scale circulation typically on days where there were these heavy precipitation events? And for the case of heavy precipitation over North Italy in autumn, then if we look at composites of vapor transport and composites of geopotential height, these are the patterns we get. So the fields are just showing anomaly composites. So we've got high vapor transport over the Mediterranean, and we've got this sort of Rossby wave train here in geopotential height. And then we define precursors based on these composites algorithmically, which focus on statistically significant anomalies that are large in amplitude and that are spatially coherent. And the black contours show the region that our algorithm selects for this particular case as the part of that composite that we think is a sort of physically interesting driver to look at and conditioning variable to look at. And so the advantage of doing something like this is we can take this big, messy ensemble of fields, and we can reduce it to something a lot more interpretable like this. So what I'm showing here is I've projected in my forecast, I've said, well, how much does the forecast for each member on a particular day in the forecast look like this pattern? And so in geopotential height, so over here, we have cases where this wave train pattern is strong. There's this cyclone here and an anticyclone here. And for the negative anomalies, we'd have a reversed pattern where there's a ridge here and a trough here. And then for zonal flows, it'd be in the sort of neutral middle. So this is measuring the activity of that wave train pattern. And then on the y-axis, we're looking at, it's the same story, but for this vapor transport anomaly. So up here, we've got large, basically signatures of atmospheric rivers in the Mediterranean. And down here, we have like strongly suppressed moisture, so very still conditions or very dry conditions over the Mediterranean. And okay, so this already gives us a lot more information than the previous slide did. So we can see this forecast evolves fairly coherently for the first sort of 8 days or so, with this wave train growing in amplitude. And then in the ensemble mean, which is shown in the thick black line, there's a slight increase in vapor transport. It's about a standard deviation more than normal, but nothing that you'd say is like really, really high risk. But already you can see that there are some ensemble members, there's about 10, that go to really quite, they get quite a strong vapor transport signal. So that's a three standard deviation normally for some of those. And in background shading, we've got some sort of flow-dependent climatology of heavy precipitation over North Italy. And so when you're in this top right corner where you have the strong wave train and you have the strong vapor transport, you've got a very elevated risk of extreme events. So this would then indicate a forecast that you're not going to do anything drastic.
Sorry, Joshua, can you what lead times are you?
That's a
15 days or the 15 days of the forecast? No?
that is in total a 9-day forecast, and I think that turning point stays 7.
Okay.
Yeah. So we're mostly so the extended range, and this is a bit closer borderline, but yeah. Yes. So in this case, we're looking at sort of a scenario that would be taking place next week, or just the beginning of the week after. And you're not going to do anything drastic based on this forecast, but you're going to make sure that you check first thing tomorrow how this scenario is advanced.
This is for the period of the flooding in Lavagna, May 2023.
Okay.
So
Yes, I actually should have buried the lead there. This is for so there did end up being a quite high, or a very high impact event on that, as it turned out. And we'll come back to that case maybe later. Okay, so I've sort of explained this already, but this is how we sort of define our precursors. So we pick our region, we identify patterns in different large-scale variables, filter them using those criteria I mentioned before, and then we project those onto daily variability fields. So it's the same way you'd construct an NAO index or something like that, but now we've got specific patterns for each region and each season that are closely linked to extreme rainfall events. And this is not a deterministic relationship by any means. I think this is just showing a sort of flow-dependent probability of having a 90th percentile rainfall event as this trough wave index is stronger or weaker. And even for very, very, very strong wave trains, we've got a 5 or 6 times increase in the probability over climatology of having such an event, but it's never going to be 1-to-1. And that's because we're primarily focusing here on larger scale synoptic features. They sort of set the stage for an extreme event, but it's the mesoscale systems that have to sort of dance on that stage if you want to actually get extreme. So that's just something to keep in mind here. So this is a probabilistic shift in the probabilities of the distribution.
Sorry, can you explain this?
Yeah, on the right, on the left. The left. Okay, so I've just fitted. So this is a distribution of this wave train index when there were no heavy rainfall events. And then this is a distribution of the index when there were heavy rainfall events. And then I've just fitted a logistic regression, and that's what the blue line is. Yeah. Okay. So we could talk about what, so that's, I've talked about it but what's it good for? So one of the first things we looked at was how it could be used in a sort of real-time forecasting context. And it just so happened we were sort of playing around with that, investigating that when there was this extreme flooding event in 2023, in May 2023. So here we're just seeing the spatial pattern of heavy precipitation during that event. This is just a time series averaged over that red box. So between the beginning of the 16th and midday on the 17th, I think it is, there was sort of 2 big spikes in precipitation that led to a lot of flooding. And that's associated with this storm Minerva, the cyclone here, that had very strong southerlies up into the Adriatic and then easterlies into Emilia-Romagna. And here's the vapor transport in red, so we can see this strong moisture transport as well. So the storyline of this event is quite interesting. So maybe just start by going through the sort of meteorology of what actually happened. Why was there this event? So on the 10th of May, there was quite a strong cyclogenesis in the Labrador Sea. And this drove the downstream to the building of a ridge on the 11th. And it built that ridge so fast and so steeply that it sort of almost immediately broke on the 12th. And that led to this formation of this cutoff low here over Europe. And that cutoff low sort of was associated with an anomaly in the low-level jet that on the 14th had like strong northerly flow down towards the coast of Morocco and then westerlies over the Atlas Mountains. And because we had these strong westerlies over the Atlas Mountains, we had some lee cyclogenesis happening on the east of that, and that is what turned out to be Storm Minerva and spun up that storm. And because also there were these anticyclones on either side, these ridges, I think this kind of progressed relatively slowly, and so led to it dumping out a lot of moisture. Okay, so that was how the event actually occurred. So how well was the event predicted? Here I'm just looking at the Eastern WF forecast. So here this is a forecast evolution plot. We're looking at rainfall averaged over North Italy on the 16th of May. And the x-axis is showing ensemble forecasts for different lead times. So this is a sort of 12-hour forecast, and this is a 12-day forecast. And we're looking at the distribution of the ensemble, and the blue line is showing Era 5 validation, and the black is the ensemble mean, and we can ignore the red line. And what we see here is we had about 2.5 days of fairly confident prediction. And there were 2 days before that, so maybe back to sort of 4.5 days beforehand, where there was sort of strong shift in the ensemble towards generating extreme rainfall, but with a lot of uncertainty, right? There were still a lot of members there with no rainfall. And then before that, there really wasn't any signal in precipitation.
Like a bimodal, focused bimodal solution on the 5th. Huh?
Yeah.
In the sense that there are many showing kind of heavy events and some other group below.
Exactly right. Yeah. So, okay, that's not too bad. 4 days predictability is not too bad. And we might say, well, maybe that's as good as well as we could do, since this was quite a, quite an extreme event. So, maybe it's rainfall, so not that easy to predict. But there's some indication that, well, we had some indication that this was at least a high risk event further ahead, a little earlier than this direct forecast suggests. Because still looking in the IFS, we also were monitoring the evolution of the Z500 precursor index and this vapor transport precursor index in the forecasts. And so here we're looking at the wave train, and already on the 8th, so that's 8 days ahead, the forecast was fairly confident that there was going to be a wave train pattern in place over North Italy, which obviously is not a sufficient condition for extreme rainfall, but already was a sort of preconditioning. And we were sort of saying at that time, okay, let's like keep our eye on that, so that could be an interesting case. And then on the 12th, well, sort of on the 10th and the 11th, no, sorry, the 11th and the 12th, there was a an increase in the number of members that were predicting this high vapor transport precursor, anywhere between 3 and even in some members up to sort of 5 standard deviations above normal. In the end, this ended up verifying that about 2 3/4 standard deviations, maybe not the worst possible event actually occurred. And so, yeah, there was some like first early warning signs, and then our first emails discussing this case were actually on the 9th. So that's sort of just to say that if you want to catch the early warning signs of extremes in the ensemble, then looking at the direct forecast variable alone means you're not going to necessarily catch every case, whereas looking at these sort of necessary but not sufficient conditions can help you build a longer term perspective on how the events are developing. And we can also use this to sort of ask questions that are quite interesting for, I think, from a scientific perspective, but also are helpful for when reasoning about the forecast. It is saying, okay, well, the forecast is uncertain. Why is the forecast uncertain? And so when do we think it will become certain? And so here we did an ensemble sensitivity analysis where we took the ensemble members that had high vapor transport, and we took the ensemble members that had low vapor transport 4 days ahead. And we said, well, what's the difference between them? And of course, at near verification time, the difference between them is, well, one of them has a big cyclone and one doesn't. So that's not very interesting. But if we sort of track that back further, 4 days after forecast initiation, it's about how this Rossby wave breaking occurs, or rather doesn't occur. Because in the members with lots of vapor transport, you can see there's this cutoff low is formed. We've got this closed contour, geopotential height here, whereas that was not the case for the members that didn't have the vapor transport. So the wave didn't really break, it just kind of wobbled. So why did one wave break and one wave wobble? Well, ultimately that came down to exactly where that cyclone over the Ecuador Sea was. Was it slightly to the west or slightly to the east? And uncertainty in the position of that cyclone is the difference between the two ensembles, the one that's very dry and the one that's very wet. So we were able to say, okay, well, when that cyclogenesis actually occurs, then we should have more forecast confidence, and that's basically what we saw. Okay, so yeah, that was what we were doing on forecasting. More recently, we've been trying to see, well, that was like for a class of events. So we defined our precursors for all heavy rainfall events in North Italy, and we used it to study this case. But sometimes you have cases that don't really look like the typical flow. And you might, and especially for the very most extreme events, you might want to see, well, is there something we can do for individual events? I don't want to have to think about a class of event, but maybe an event we've only seen 1 or 2 times. So is there a way to try and understand such events? So this is something I did in a paper with Gabriele Mazzori. We basically kind of extended our approach to now identify patterns based on individual events. And we did 3 cases, and the one I'm showing here is for the LA wildfires in 2025. So, and again, we have an algorithm which identifies high amplitude, spatially coherent anomalies that lie close to the region where the extreme occurred. So we're not necessarily going to isolate always fully causal features, but in general, the typical approach in dynamic attribution is just to do a box and say, well, let's look at the variables in this box around the domain of interest, and we think this is maybe a slight advance on that approach. And we've looked, and so in this case, for these wildfires are associated with a strong ridge over California and a cutoff low over Baja California, which drove these strong easterlies, these Santa Ana winds that have a lot of descent, so those katabatic, dry, hot winds that really precondition for forest fires. And we looked at windstorm Kieran, which unsurprisingly was associated with a strong cyclonic anomaly and a strong wind speed anomalies at the low level. And we also looked at the Valencia 2024 floods, which was this classic cut-off low pattern with strong southerlies out of North Africa that moisten rapidly over the Mediterranean, and then strong easterlies bringing that into the coast of Spain and lead to, and there's a lot of ascent there along the coast. So we looked at these 3 cases, we sort of applied this approach to all of them. Let's get this. Yeah. And so what do we learn? So, for example, it turns out that forest fires over, well, I should say fire weather conditions over California have become 55% more likely in the last, between the first half of Era 5 and the previous half, the second half. So we kind of knew that already, that forest fires going up. But what we found was that of that 55%, about 10% is coming from dynamical changes. These ridges and the associated easterlies are actually becoming more frequent. So we don't think that was previously known, as far as we're aware. So that's quite interesting. So then we're able to apportion that between the dynamical and the local conversion processes. Oh yeah, and we can also look at that as in a sort of flow dependent way. So on the x-axis here, over to the right here, we're looking at cases that are more typical. They're closer to that LA 2025 case. The flow looks like this. And on the left, we've got flows that look very different to that 2025 case. And on the y-axis, we've got the chance of having high fire weather conditions. And so we can see the black line is for all of Era 5. The more that the conditions look like what we saw in 2025, the more likely it is you have high fire weather. So that's a nice sanity check in our approach. But the really interesting thing is if you look at conditions that look nothing like, so to neutral conditions, they don't have a strong projection onto our dynamical patterns. In the first half of Era 5, which is shown in light blue, it was basically impossible to have high fire weather over California without that ridge and without those Santa Ana easterlies. In the second half of Era 5, it's very much possible to have them, and in fact they happen quite often. So we're also able to see sort of violations of our own hypothesis here. So when we see that actually you don't need this pattern to cause high fire weather anymore, whereas you used to in the past. So that was quite interesting. I'm going to skip over some of this. The validity of flood was very interesting meteorologically, and unfortunately, at least from our perspective, seemed to be a complete null result in terms of climate signals. We didn't get any change in that. I've seen a few studies that sort of have slightly different answers on that, but we don't find any change in either the chance of having the heavy rainfall when the conditions are in place or in the conditions themselves.
This is the Valencia flood or what?
This is Valencia 2024, yeah.
Each convection was.
I want to show you
a big road, so.
Yes. But we didn't see that there was any more. I mean, it could just be a limit of the observational record. But we didn't see evidence that. And we used, we were only interested in like very high rainfall. So we were looking at accumulation of rainfall over the 99th percentile. So we didn't care if it had lots of drizzle, right? We wanted it to have high rainfall totals, and we don't get any change. Some studies have shown some change, but they were just looking at total average rainfall. So, and since I've been in Bergen, I've mostly been looking at how we can use these ideas to understand what climate models are doing. So we've been looking at in two large ensembles, the CSM and MPI large ensembles, how heavy precipitation is represented in 38 different European regions and 4 different seasons, and trying to understand, where are their biases, why, what scales and flows do they come from, and how does that impact their trend. How am I doing for time? Yeah. So I've kind of gone over most of this. So here what we do now in this work of the climate models is once we've got some precursor indices for a particular region, we convert those into a single index S. We just take the first principal component. So we combine our Z500 or our U and V850 information into a single index we call S. And then we sort of discretize. So we break S into 10 bins, and then we look at the chance of heavy precipitation in each of those bins, and we look at the occurrence of those bins. So for example, here we've got the 20% of days that have the strongest value of S, and then this is in iMerge data. We can see that the chance of heavy precipitation is indeed very elevated, about 7 times higher than normal over Southwest Siberia when this particular sort of omega blocking patterns in place in winter time. Whereas if we look at the 20% of days with the most negative projection onto that precursor pattern. So it's a ridge instead of a cyclone off the west coast of Spain. It's basically impossible to have heavy precipitation. So, okay, another good sanity check. So we look at these quantities in year 5, we look at them in our climate models, and we try and understand the differences. Okay, so I'll try and motivate this through a couple of case examples. So this plot here is showing biases in heavy precipitation occurrence in TSM and MPI large ensembles in wintertime. And there's lots happening here, but I just want to look in the southwest Iberia region, where the two models have different biases. So MPI is slightly too wet, and CSM is a fair bit too dry. So why? Why are the two models different? Can we learn anything about the model's behavior from understanding this difference? And if I wanted to do some regional downscaling, which model would I want to pick to force my regional model? And how could we eliminate these biases? So those are sort of questions we want to tackle. So we can do it like this. So we say, well, the overall chance of having heavy precipitation in the model is the chance of having each of the different flow patterns, the different bins of S, and then it's the conditional probability of heavy rainfall within each bin. Okay, it's basic maths. So let's take that turn by turn. So if we look at the chance of having these different large-scale conditions, in era 5, this is done by decile. So every decile of the synoptic index occurs 10% of the time by construction. MPI, however, is producing these strong omega-blocking patterns about 18% of the time, so 10% of the time, almost twice as often as they should. Whereas CSM is sort of got the opposite story, so it has way too few of these omega-blocking patterns. And I should say, this large ensemble, we've got many members, so our uncertainty estimates are pretty tight there. So, okay, based on this, we'd expect MPI to be wet and CSM to be dry. So, but is that the whole story? No, so it's the other half of the equation. So if we look at the chance of having heavy precipitation as a function of the synoptic index, the black line showing era 5, and we can see this is very strong conditioning. So the majority of the heavy precipitation events occur in just these sorts of top 2 bins. CSM does a reasonably good job of emulating that, but it struggles to produce enough heavy precipitation for the very strongest omega blocking patterns, whereas MPI kind of struggles across the board to produce heavy precipitation. So we can aggregate that, and the net result, we can do a budget of the biases in the model. And we can say, okay, like I showed before, CSM is a bit too dry, MPI is a bit too wet. And now we can see, though, that that's the cases here are quite different. So for CSM, the dynamical bias and this bias in the conversion to a surface hazard are additive. They compound each other. It's too dry on both accounts. Whereas MPI has a cancellation or partial cancellation of biases. It has way too many blocks, way too many lows that should produce precipitation, and none of them are, or not many of them are producing extreme rainfall. So we've got two quite different cases there. And if you were to sort of downscale MPI, for example, you might say, well, its overall bias is less, so I'll downscale that. You're probably going to eliminate a lot of this bias, and you'll be left with this bias. You're going to have spent a lot of compute and money and time and not had a very good simulation out of it. So that would be an expensive mistake to make. So if you want to gain a sort of more holistic understanding, you can sort of categorize these biases because they have these different implications for different applications. So we can say, here I'm plotting the size of the conversion bias on the x-axis and the size of the dynamical bias on the y-axis. And we've added some colorful sections to that phase space. So you could either have biases that are almost purely to do with conversion errors, purely to do with dynamical errors, compounding biases of different types, or cancelling or compensating biases of different types. And this dashed diagonal here is a line of constant net zero bias. So if you lie somewhere along that line, your model looks great, as long as you don't disaggregate it by different light conditions. And on the right, we're just showing the category that each of these models falls into for each of these regions. And we can sort of see the main point I want to make right now is that these compensating biases are common. So I didn't pick a pathological case. This happens all the time. So that's something to bear in mind. And if you want a more quantitative perspective, you can, of course, look at maps of the dynamical bias and the conversion bias. How did I do this? Oh, yeah. So I want to bring this back to the North Italian case because actually both these models can't simulate heavy precipitation in autumn in North Italy. That's not exactly surprising because at 1.5 or 2 degrees, they hardly have an Adriatic, they don't really have Apennines, they don't have mesoscale collective systems, and there's probably loads of other stuff they don't have that I can't think of right now. And we can see that here, that their net bias is like 90% too little heavy precipitation. And that's almost entirely to do with conversion errors. So they just don't, whatever the dynamical conditions are doing, they don't create that heavy precipitation on a local scale. So if you want to understand the future of extreme precipitation in North Italy, you should probably, the obvious thing to do would be to say, well, I can't look at these large ensembles, right? I need my super high resolution models. And they're obviously great, but these large ensembles are the best understanding we have of internal variability of the atmosphere, the slow scale multi-decadal variability in different scenarios. It would be really nice if we could still learn something from them. And in fact, we can, because there's nothing super wrong with their dynamics. They can generate these wave train patterns that cause or that precondition for heavy precipitation in North Italy. They just can't do anything with them. So we can say, well, all right, I don't trust any of the predictions of this model for actually producing the heavy precipitation, but I can at least think about the change in heavy precipitation implied by the change in their large scale dynamics. And then both models predict to different degrees, but they both predict a slight decrease in these autumn Rossby wave trains. It's an overall zonalization of the flow. So we can use that model. We can use that information from the model. And if we then have a convection permitting simulation and we think we can nicely constrain the conversion processes, because this equation is all very quantitative, we can splice those results together. So I don't have a plot for that, but that is what I'm working on at the moment, is trying to combine information from large ensembles with along the scale simulations in a quantitative way. How am I on time? I'm pretty much up, right? Do we know? When did I start? Do you know what? I will stop there. So that's pretty much. So we've worked on them. Yeah, we've built a framework for identifying the extreme relevant dynamics, which we've applied to lots of different contexts and different scales, and we think is a nice way of gaining extra information from these simulations. The fundamental tool for doing that, this Domino, we have a Python package called Domino, which allows you to compute these precursors and do things with them. That's all on GitHub and it's relatively easy to use, so I invite you to check it out. We also, all these plots are on, we have a little website for that I forgot to put the QR code in, but we have I can send that around maybe. We have a website so you can visualize and explore the different biases and trends in these different climate models. And we have this set up in a nice little pipeline. So hopefully, well, this summer, CMIP 7 fast track results should come out, and we're going to have results on our website a week or two after that. So we'll have sort of first flow dependent analysis of extreme rainfall in CMIP 7 fast track, hopefully by the autumn. So that'd be nice. Yeah, so thanks for listening and questions welcome. Thank you.
Also the schema, the general schema explaining